Let's dive into our technical program. We have an exciting plenary today, which will be presented, which will be introduced by Aaron Partridge.
Good morning. I'm happy to see everybody has gotten in here. So as you just heard, it's the common practice for an advisor to introduce his student in a meeting like this. So this is the other way around. I am Tom's student, and he was my advisor. So that's a real pleasure for me to have a chance to introduce Tom. Let's see. Let me do two things. I'm going to start with sort of a formal background and then tell you a little bit of a story to start his talk off. So Tom Canty received the PhD degree in physics from UC Berkeley in 1989, and from 89 to 93, he was with JPL, where he worked on electron tunneling high-resolution microsensors. In 1994, he joined the Department of Mechanical Engineering at Stanford, where he directs the microcenter-based research on resonator, wafer-scale packaging, cantilever beam, force sensors, microfluidics, and novel fabrication techniques. He was a founder and CTO of Coology, a microfluidics chip cooling component manufacturer, and a founder at SiTime. He is also a founder and board member of Applaud Medical, which is currently developing non-invasive therapies for kidney stones. He's authored and co-authored over 250 scientific papers and holds 50 patents and has advised more than 60 PhD students. Now, along the way, he's had some unusual experiences, opportunities, including being part of a team that won the 1999 National Championship and the 2000 World Championship in Ultimate Frisbee, co-ed division. From 2006 to 2010, he was program manager at the Microsystems Technology Office at DARPA, where he led programs in thermal management, nanofabrication, manipulation of the Casimir force, and the DARPA Young Faculty Award. And recently, he's been appointed as the Senior Associate Dean for Engineering Student Affairs at Stanford. Now, I first met Tom in 1989 while he was at JPL, and I was down there for a conference. I was building something called a ballistic electron emission microscope, and we were tunneling electrons between platinum and gold, and trying our very best to eliminate environmental influences from this piece of equipment. Tom, on the other hand, was tunneling electrons from one piece of gold to another piece of gold, and he said, wait a minute, maybe there's something I can do here. And he was building accelerometers and trying his best to make as much environmental influence as possible, making some incredible micro-G accelerometers with this same technology. So now here we are 30 years later. My colleagues and I are trying to build MEMS oscillators with absolutely the minimum amount of environmental influence possible. And Tom says, well, wait a minute, maybe we can do something with this. So we're going to hear today about that, about doing what we do in exact reverse is how I think about it. So with that, welcome to Tom.
Thank you. So thanks for that kind introduction. Someday I hope to have a chance to introduce Aaron and tell a few stories that would be entertaining as well. And thanks to Dana, Aaron, and the organizers. It's a great honor for me to be here for this conference, here to meet old friends and new friends, and to have a chance to tell a little story about some of the work my group's been up to over the last decade or more, relating to many of the topics that are of interest to this community. So I'm going to tell a little story. It talks about some of the challenges and issues we face in trying to make precision time references, and how those same lessons have helped us understand perhaps how to make precision inertial sensors, and how the sort of combination of all that experience is actually now feeding back into our thoughts about the time reference side of the equation. We've had the luxury of a long and steady support from DARPA, a number of different programs that have kind of kept us sort of equipped and resourced to focus on all of this as we've gone through it. And it's been an exciting time. I should also mention Liz Maria Camencho-Ortiz and Jenna Rodriguez are here for my group down in the front row, participants and supporters of this effort. And I'll be showing some of their work a little bit later on. So maybe just to set the stage, and we talked about this a little bit last night at the rump session, and maybe at every break and in every meeting between any pair of people in this room, we're faced with this interesting challenge of wanting high performance time references that could be smaller, cheaper, and even better performance than what's currently available. And the spectrum of what's out, ranges from very, very high performance cesium clocks that are ballpark $100,000 or more, weigh 30 kilograms, consume more than 50 watts, and over temperature have accuracy that's better than in the 10 to the minus 13 range. OCXOs, these are ovenized quartz crystal products that are a fair bit smaller, basically a factor of 1,000 smaller, factor of 10 less power, factor of 100 less cost, and maybe a factor of 1,000 or 10,000 less performance. And so you sort of work your way down the performance cost curve. And then more recently, silicon micromechanical oscillators have come up, and we'll hear a bit more about that later today. But SiTime has a product that weighs milligrams, consumes microwatts, costs less than $1, and can get down close to close to 10 minus 9 in terms of long-term stability. And like I say, I'll let them quote the details on that. Clark wrote a paper about a decade ago that sort of outlines the challenge and the opportunity that is presented here, that there's potential for micromechanical oscillators to perhaps reach stabilities down to the 10 to the minus 9 range and provide low cost, low power, and other opportunities. But aging rates will probably not match those of atomic clocks, just based on what we think is true for MEMS. At the same time, atomic clocks are too big and too expensive, and unless they come down and become portable and accessible to sort of things that we might carry around with us, there's always going to be this gap between the performance of one and the other, and we really have incredible needs right in between. So can we improve this? Of course, there's been effort on the chip-scale atomic clock program. The current version of this that I could find on the web is 100 grams, 300 milliwatts, I'm guessing around $1,000, and has long-term stability over temperature that's better than 10 to the minus 9, but not a whole lot better. And I'll say a little bit later today about what could be an in-chip OCXO technology for MEMS that is approaching some of these parameters, but is a fair bit smaller and could be a lot less expensive. So that'll be sort of the frame for the timing part of this talk. If we talk about inertial sensors, it's actually a pretty similar set of problems and challenges. I think a lot of you would recognize this conflict between the very high performance, high cost, high tech instruments that are used for precision navigation and the things that are more representative of the inertial sensors that are in your pocket in the smartphones and watches. Northrop Grumman makes a hemispherical resonator out of quartz. It's a precision engineered mechanical object. It costs a lot of money to make. There's a lot of tuning and control applied to it. The final product weighs kilograms and consumes watts and costs thousands of dollars. But it can get to stability as a gyro down to 0.01 degrees per hour, which is what you need for certain applications in navigation. The MEMS complements to this are milligrams, milliwatts, and less than $1, often a fair bit less than $1. Their stability is about 500 times worse. And once again, we sort of have this gap that what we would like is for the MEMS devices to approach the performance of the navigation applications, but we're struggling with how to get there. And I think true for both timing and for inertial navigation, the issues that limit the low cost, low performance things are not physics. It's not Boltzmann's constant and temperature and things like that. It really comes down to more practical things, packaging, temperature, stress relaxation. And I think what's interesting is that it's the same pile of issues that affect both of these communities. And that's why I think it's interesting to look at the lessons being learned in parallel. If we could make better inertial sensors and have them still be portable and low cost, it opens up a whole lot of applications that are currently inaccessible. We'd like to do much better job of personal navigation. There could be better use of these systems in autonomous vehicles and in safety systems. There's a lot of interest in virtual reality, but that also could be much better. This could lead to improvements in surgery. Surgeons would like to be able to see things that are not readily visible to them while they're doing precision operations. And there's a long list of DoD applications, which is fortunate because that means there's also funding to work on this. But as I said, with the case of the low-cost timing products, the basic issues here are not physics. It's more practical things. It's materials, it's drift, it's aging. And I think, so the lesson for today is really to talk about what we've learned sort of from both sides of this and how they might start to come together and help us do a better job on both sets of problems. So I'm going to start off talking about resonators and some things that we've learned over the last decade and longer. Try to explore a little bit about how we've solved some of those problems. Say a little bit about what's been going on more recently in the community and in my group with the inertial sensor side of this, trying to adapt the same sets of lessons back across that interface. And then finally, I'm going to go back to the resonators and see if everything we've learned along this trail actually helps us build a better OCXO and what's the potential for that technology in the future. So MEMS has been around a long time. And I think even in this community, there's been a raging debate that goes back 20 years or more about whether MEMS versus quartz will ever work out in a favorable way to the MEMS community. The very earliest work is more than 50 years back, the Resonant Gate Transistor from Harvey Nathason and his group. It was a gold beam built on a very primitive integrated circuit. The oscillation of the beam and the vertical axis was detectable by looking at the properties of the transistor position right underneath it. It had a lot of issues, but it was actually pretty promising in its early stage. Its characteristics over temperature were dominated by the mechanical characteristics of the gold beam, which were terrible. But therefore, or nevertheless, somewhat encouraging even back then. Very quickly, there was work on making beams out of silicon. This is now 50 years old. And right away, you could see that the basic performance of the device was significantly improved. The temperature coefficient of the mechanical properties of the silicon was much better than that of the gold. And this was considered a very which, again, 50 years ago, I think set the stage for what then became a very long, painful development process within our community to try to solve the problems that would fix both what you see here, the strong temperature dependence of frequency, and all of the issues with uncertainty and drift. This work went on for many, many years in the MEMS community. There was studies by researchers all over the world on micromechanical devices, mostly cantilever beam resonators, exploring things that would affect the resonant frequency of that device. There was interest from the start in detecting single atom or single molecule absorption on these cantilevers as a way of making sensors. And in order for that application to be useful, the resonator had to be stable enough that the frequency shift from a single molecule was detectable above the background drift of the resonant frequency. So there was a lot of interest in this. People built a lot of devices and turned them on and let them run for a long time. And the general sort of legend in the MEMS community was that, try as we might, there seemed to be some inherent aging problems with the technologies that we were playing with, that the materials were relaxing or creeping. There were other kinds of aging phenomena happening. And even as we got better at building devices and building packaging, we still consistently had this problem that the resonant frequency of standard micromechanical elements, when even packaged to the best that we could package at that time and protect from the environment, we still saw drift in the dynamic properties on the order of parts per million per month. And you can see here, of course, anything that's drifting at the level of parts per million per month is pretty much useless in this community. It's just not, that's a non-starter. And the two examples here, there are two silicon resonators, both in the wafer level package, one using thick films, one wafer bonding, but both clearly exhibiting aging phenomena that would be incompatible with any real-time reference that we might want to build. And the way the community was talking about this was as if it was a fundamental inherent property of the MEMS. That something about the cantilevers, the materials, the multi-layers, maybe the oxide layers in the MEMS process were causing some aging phenomena. That the silicon material and maybe the oxides it was grown on were the source of some kind of interfacial aging, some other kinds of phenomena. And that you might be able to get by if you have time and resources to do month-long burn-ins, maybe over high temperatures, do cycles, and then perhaps whatever this random stuff that was going on, it would be settled down enough that you could then move on and do more interesting things. Now, I think if this is your approach to making a stable mechanical technology, that you're relying on burn-in to solve a mysterious problem, you're really doomed. That problem is not going to go away. It'll come back when you least want it. It'll resurface somehow as you do temperature cycles or expose your system to some other kind of stimulus that you haven't tested. You don't know how to accelerate this. You don't know anything about the physics of it. It's really not a good place to be. And I think this is, so 20 years ago, even maybe a decade ago, this was sort of the general conclusion about MEMS. You can do pretty well, but you can't make really good stable references because of these mysterious inherent aging processes in them. Now we did make a lot of stuff in MEMS. We made a lot of automotive safety systems. You've been driving cars for 20 years that have devices based on this technology. And for almost a decade, all your smartphones and a lot of other wearables have had devices based on this. And we've gotten more and more sophisticated in how we build the devices, how we operate and extract the very, very small differential capacitive signals that emerge from these technologies. And it's really quite amazing. In a modern gyroscope, you're measuring forces that are down, way, way down into the attonewtons, piconewton range. Generally, certainly femtonewtons is what we're talking about with a lot of these technologies. You're able to measure displacements in these differential capacitive systems down to fractions of an angstrom. And you do this in a device that's manufactured at cost less than $1, that can survive huge temperature extremes, ride around in your car, operate for 10 years, and never fail. So there's great stuff here, but the drift is still there. And the question is it the silicon itself, or is it all this other stuff? You've got multiple layers of things. You've got all kinds of thermal expansion mismatches. You've got stress relaxations, all kinds of temperature budgets. There's getters in here that have some amount of trapped chemistry that is either present or absent. And we know, even from work that my group did a while ago, that if you have a simple micromechanical strain sensor, like a double-ended tuning fork with a pair of anchors that's attached to the substrate, the frequency over temperature characteristic that you can measure with that device can be overwhelmed by things outside the die. So in this case, the double-ended tuning fork chip is glued down onto a copper lead frame in a standard electronics package with some epoxy. And when that's the case, the temperature coefficient of frequency is minus 180 ppm per C. If we float the die and sort of relax that contact so it's really just all by itself, the temperature coefficient matches what you'd expect for silicon, more like minus 31 ppm per degree C. So it's pretty obvious that a lot of the kinds of things you want to build in the MEMS community can be overwhelmed by the stresses that get into the MEMS device from the other layers of the package. And you have to be thinking about that all the time if you really want to overcome issues associated with package stress and so on. The folks in the inertial sensor world have been paying a lot of attention to this over the last decade because they do want to make better inertial sensors. They're trying to understand the boundary between what's inherent in their technology and what's a consequence of the way they stack it up. A group from Analog Devices did a really nice and thorough job presenting a paper which then published in JMEMS a couple of years ago, where they do a very careful job of looking at not just the die, but all of the layers around the die, including the package that is glued onto, the copper lead frame, the plastic encapsulant that is built around that die to protect it from later abuse and handling. They built a comprehensive 5-element model of the whole system and then began experimenting in the model with what kinds of changes could they make that would improve the offset performance. And really the main points here is that they go through a manufacturing process where the last step cures an encapsulant which seals the whole system in a very practical and useful way, but it exerts enormous stress on the die. It's compressing the die from all axes. The die is also glued onto a copper lead frame. That glue, that adhesive underneath the die has its own properties. The lead frame has its own properties. As you temperature cycle this thing, or even just take it down from its sealing temperature to operating temperatures, there's enormous differential stresses that come in from this. And in addition to just stressing the die, they will warp the die, twist it and flex it in ways that are really sort of detrimental to the performance. So they did a lot with simulation in this approach. They played around with the design of the resonator. In this case, it's a gyroscope, but it's basically a resonator. Played around with certain aspects of the material selection. We're able to improve the situation by about a factor of 10 or more. Among the things that they did, if you look at the image on the right, the upper image on the right is a picture of the whole die, including the integrated circuit, and then the lower image is a zoom-in section of the lower sort of left quadrant of the MEMS device. And among other things they did that I think will come back as a lesson over and over again as we look through other examples, they took all of the anchors that support the micromechanical resonator and they pushed those as close together and as close to the center of the whole die as possible. If you're going to be attached to a warped substrate, your best hope for eliminating that problem is to sort of limit the range of that substrate that you're attached to the smallest possible footprint. And that's a lesson that we've learned for other applications, and I think it's interesting that it shows up as one of the dominant outcomes of this work. So we still build a lot of MEMS devices using conventional wafer bonding techniques. This is a 15-year-old picture from Bosch that I got from Marcus Lutz. There's been some improvements. There's still a lot of similarity to what's shown here. You have a tiny micromechanical element enclosed in a fairly large chamber, covered with a bonded wafer that's sealed with a glass fret around the perimeter. And if this die, you imagine the substrate now being subjected to this warpage and stress that we've been talking about. That stress will concentrate at the corners of the bonding between that cap and the substrate, creating enormous focus stresses on that glass frit seal. There's temperature cycles which cause oscillations in that. This is bad. It's going to fail. It takes up a lot of space on the die. It creates other kinds of problems. So this is kind of current technology, but it's something really we've been inspired to try to improve on. And the story on that really began almost 20 years ago when Marcus came to Palo Alto. Bosch opened a research lab in our neighborhood. Marcus had some ideas for getting rid of this sort of contraption approach to making MEMS. He had, at least when I first saw it, was on scraps of paper. He'd already filed some patents, of course, which was a good thing. Allowed us to talk together. But the objective of this wasn't anything beyond just trying to minimize the footprint. Get rid of all of this wasted real estate around the micromechanical element that's important and try to make the entire die smaller. It was really just about putting more die on a wafer, reducing cost, and perhaps improving some of the other reliability issues. This led to some research. Aaron Partridge was a PhD student in the group at the time. It led to building, instead of bonded wafer encapsulation, we started growing film encapsulation. So instead of putting a second wafer on top of the first wafer, figuring out how to glue them together, we build up the package by growing layers on top of the silicon wafer based on materials that we had access to. Bosch at the time had developed a process for low-stress, thick polysilicon, the so-called Epi-Poly. We had an Epi reactor in the lab at Stanford, which wasn't designed for this purpose, but could be adapted to do this job. And so we started growing packages by building layers on top of the MEMS technology and seeing what we could do with this. And we knew right away the goal initially was to make accelerometers, make them small, and not otherwise destroy the performance, and we had some good success with that. But we knew right from the start that anything we built had some stability issues. The resonators that we could build in the same process had this drift that I showed earlier, and it had to do with the sealing process. We're using a chemical vapor deposition oxide to sort of plug up all the holes in the top layer at the last step of the process. When that's finished, that leaves a lot of organic materials bouncing around inside the package. It leaves some organic residue perhaps on the micromechanical elements. That ages over time. It's problematic. But we did have an early victory in that we were able to make a smaller MEMS technology. We basically made a device that had exactly the same micromechanical structure as the Bosch production gyroscope of that time. We made it in this process, so it didn't need all of the wasted real estate of the bond ring, and it was substantially smaller. Had all the other same properties. In fact, from an electric test perspective, you couldn't tell them apart. So we thought this was terrific. Bosch was less interested, sadly. I think, frankly, they had a certain size fab, and they had a certain size customer, and if we put more die on a wafer, it meant less wafers going through the fab, and they'd already paid all the fixed costs of this whole thing, so there was no point in taking this thing on. Plus, it was different and complicated, and they were risk-averse at Bosch. So we were kind of stuck, looking for what to do with ourselves. Aaron was graduating. Marcus was being told it was time to go back to Germany. We were trying to decide what would be the next step for us. And Clark came out in his time at DARPA with a BAA that actually gave us a new opportunity to rethink what we were doing. He asked for wafer-level encapsulation strategies, and we had something that sort of looked like that, that could isolate a micromechanical device from the surroundings while maintaining an environment and providing either passive or active control. And the goal of this, way back then, was already thinking about how to make a miniature OCXO, how to develop a technology that could ovenize and isolate a MEMS device from its surroundings. So we knew right away that our process of sealing these devices with chemical vapor deposition oxide was never going to be good enough for the metrics of that program. So we started looking around, what other things could we use to seal the device with, still preserving this thick film encapsulation process and most of the materials. And by the way, also, wanting to be sure that whatever process we developed would be compatible with established manufacturing processes at Bosch. We didn't want to invent something that was cool and useless. So the goal was to try to develop something that actually, if we got something right and it was interesting, there's people who would know how to make more of it, and we could go down a faster channel. So among the things you could deposit, we thought about depositing metals, we thought about depositing other materials, ultra-high vacuum techniques. We already had this Epi-Poly thing that we were using to grow the first half of the cap, so it was kind of obvious to try that as well. We could just seal up the part by growing more Epi-Poly. And so let me just take you through how this sequence works as an example. We start off with a standard SOI wafer, so a device layer might be 30 or 40 microns thick. There's an oxide already there, and then a very thick handle wafer underneath that. We do plasma etching to form the boundaries of what will become the micromechanical element. We then fill in everything with oxide. This is a little unusual, but it helps us build the later steps of the encapsulation. So it fills the trenches and covers over the top surface. We then grow the first thin portion of what becomes the package. This might be 5 to 10 microns of polysilicon using this Epi-Poly process. We do some patterning of this to create access points for the electrical contacts. But otherwise, it's just polysilicon. We use an HF vapor etch to go down through the small holes in the poly and etch out the oxide that surrounds the micromechanical element. The nice thing about the HF vapor is it tends not to leave any condensation behind, so we don't have problems with capillary forces and stiction. And it's otherwise pretty clean. It leaves behind a hydrogen-terminated silicon surface, which is pretty cool. And then we go right back into the Epi reactor pretty much as quickly as we can and grow up another 10 to 20 microns of polysilicon that seals up the vents that we used for releasing the MEMS device and seals everything so that what's trapped inside is just leftover hydrogen gas and otherwise a sealed micromechanical element buried inside the wafer. We do some last steps that help us establish the electrical contacts from the surface down to the MEMS layer and do some things. We can heat the wafer in a nitrogen furnace, and that drives out the residual hydrogen, so we can reduce the pressure that's trapped within the resonator, get down to pressures that will give us higher Q. The resulting technology has a lot of properties that we wanted, in that there was low pressure and a pretty clean environment. We thought that would give us a better shot at a stable resonator. It did some things that we didn't understand at the time, but have turned out to be really important. The sealing step takes place at 1100 degrees C and takes, a half hour to an hour. So there's a very high temperature bakeout of the MEMS device during that process. It's unlike any bakeout ever seen anywhere else in the MEMS community. A lot of really good things happen when you cook something at 1100 degrees C for an hour in terms of killing the chemistry. One thing in particular, if you have hydrogen gas in an environment at that temperature and exposed silicon sidewalls, the hydrogen promotes a smoothing process that takes away what was originally the scalloped sidewalls of the etch process and replaces that with something that's almost atomically smooth. What's important there is that later on, there's no roughness or sort of unpleasant surfaces that are going to relax and age over time. The surfaces of this micromechanical element are basically in their ground state, and there won't be any further evolution in the structure. That leads to some of the really important benefits for aging. There's no native oxide here. There's no oxygen, because that high temperature seal, basically the silicon acts like a getter for anything like oxygen during the sealing process. And all that's left over is a low pressure of inert hydrogen, which is basically an ideal gas. It doesn't stick to anything, it doesn't react with anything. If there's a little bit of it bouncing around, that's perfectly fine. It's not going to do anything that would change the properties of the device. And really, I think what's important here, my degree's in physics, I have a lot of friends in chemistry. I think in general, if you're trying to do things that are precise and stable, you want to be dealing with physics and not chemistry. I don't know if there's any chemists in the room, but I think in general, chemistry has all these things that scale with temperature, with Arrhenius behavior in ways that are hard to control, hard to eliminate, hard to manage. You just don't want to have it around. And this really, the end product here is that you have a technology that leaves you just with the physics. You have a mechanical property, you have a material, it's clean, it's smooth, it doesn't age, it's a single crystal, it's one of the most well-characterized materials in the history of mankind, and it's just a really nice thing to be standing on top of. So we started building resonators and looking at their behavior, and almost right away we noticed that these things were not drifting. Now this is micromechanical element glued down onto a lead frame in an oven in a lab at Stanford over a year with all of the external environmental things going on. The gaps in the record reflect moments in the personal life history of the student Bong Sang Kim who was doing the work. He got married, had children. You can sort of see there were parts where he was gone for a week or two, and inevitably that's when things got turned off, but turned back on, everything's fine. So no aging, really exceptional stability, and gave us a platform where we could talk to Clark about our metrics, and he didn't hate us, kept funding us. Thank you very much. Appreciated that. But since we're at Stanford, we're surrounded by venture capitalists at Stanford, it sort of seemed like we ought to have a conversation about whether this was a company, whether this could be a technology. And we talked to a lot of VCs, we talked to a lot of possible partners for us, built a team, got a bunch of money, and SiTime was launched 14 years ago? A long time ago. And I'll tell you, so SiTime achieved, I think, substantial commercial success just in the last couple of years. If we'd have told the investors at the start, we have this great idea, we're going to work on it for a decade, and you're going to get your money back plus some more. Some. You know, isn't that great? It never would have happened, you know. So in the end, even though we had this great platform, there was a lot of problems that had to be solved in the company. But it's at current state, we're in a situation where, of all the things you've heard about this week at this conference, there are more actual implementations of the SiTime technology in your pockets here than anything else you've heard about. There are probably a few hundred oscillators here in the room today, and it has actually crossed into the point where it's making a difference. The technology there is a micromechanical resonator encapsulated in a process like what I've described, which can be temperature compensated because all the other drift is under control. And we're talking about levels of accuracy over temperature in the tens of parts per billion for simple TCXO technology. So it's a MEMS device, a circuit that measures temperature and corrects for the temperature coefficients of everything that's modelable and repeatable. And you'll hear more about that this afternoon from Sasan. So I don't want to dwell too much on the SiTime side of this. So we learned a lot. I think we learned how to make a micromechanical thing that could be packaged in a way that's compatible with volume manufacturing. We learned how to make it such that its mechanical and dynamic properties were very stable over time. And then the question is, can any of this apply to making inertial sensors? And so this is what we've really been working on for a lot of the last decade. And there's really two ways to make, or to talk about making better inertial sensors. You can start off with really cool ideas about how to make a device that'll sense an inertial phenomena in a new way. And that's very common in the inertial sensor community, in the MEMS community. You come up with the sort of the way to make that thing and demonstrate the first sort of functional performance of that. And you get some signals, you show a scope trace or some other thing. And right away you notice that it's pretty good, but there's some issues with drift. And then you spend the rest of your life trying to solve those drift problems by changing design, changing package, changing circuits, compensating. And that's basically representative of the technology that's in your pockets, all the inertial sensor technology. The idea for how to measure the signal came before any of the other stuff. And it's sort of, you've got a horse and a cart, and I think, frankly, they're in the wrong order here. I'd say you should start with a manufacturing process that you know solves the hardest problems you're going to face at the end, which is going to be the drift and the offsets. Focus on designs that reduce those efforts and effects as much as possible. And then, after you've got a stable thing that you know works and that you can manufacture, then go try to figure out how to make it more sensitive. Change the designs, change some levers, change some things that'll give you better sensitivity. And that's kind of the style we've been looking at this. So the things we've learned from the Resonator work that inspires our work on inertial sensors are very simple. Use the Resonator as a sensor. You know, don't make piezoresistors or other sort of weird material stacks. Stick with the Resonator, because we know we can make that stable. If your signal is now a change in frequency. Figure out ways to make that a differential frequency or other things, but start with that. Use crystalline silicon. It's easy to make things out of poly, and they're pretty good, but there's just a lot of stuff that goes on with poly that you're never going to fix. Design within this process, this Epi-Seal process that we developed, because we know it gives you a stable result. This process has constraints. It doesn't let you have arbitrarily large gaps or arbitrarily large structures or weird materials. There's no way to put a piezoelectric material into this. Live with that. And then focus on designs that are going to improve your immunity to package stress. And really simply here, this means, you know, don't have a whole bunch of anchors spread out all over the die so that when the die warps during your final assembly, that's going to stretch your mechanical part all over the place. Single anchors as much as possible. And then our goal was, if we found something that worked pretty well, we could transition to volume manufacturing. So the first question really is, can you build inertial sensors in this process? The constraints of Epi-Seal are not ideal. There's a limitation on the gap widths. You don't have a lot of materials. You generally have low pressure. And we don't know what happens if the mechanical element touches the adjacent surface. The MEMS community is plagued by stiction, which is how actually the inertial sensors in your pocket will fail someday. The mechanical element's moving around. If you drop the phone, it touches the sidewall, it might stick, and that's dead. In our case, we have atomically smooth surfaces of single crystal silicon that might come into contact. You'd think that would be a horrifying opportunity for stiction to happen. It turns out it's actually not so bad. We've looked at this a lot. We've built a lot of test structures, as many as 1,800 parts over a bunch of different runs, different geometries, different students running the process, so the actual parameters are not well controlled. We find a very consistent level of stiction force, which looks like van der Waals and not chemistry. So two things come close together. There are physical forces from van der Waals that will bind them together. There's a finite size. If you exert a force big enough to overcome that, they'll come back apart. And again, this is one of these things where if you have a choice between a problem that depends on chemistry or physics, take the physics. The nice thing about van der Waals force and adhesion is we know exactly how big this force is going to be, and that's just a design problem. We can build inertial sensors that have enough restoring force to overcome this adhesion, which is lovely. So this is what we've been doing. And then since then, we've made some modifications to our process because we need better resonators than the basic SiTime process can produce. In particular, we'd like to have things such as Lame mode resonators or with sort of bulk extensional modes because they have higher Q and higher frequency and generally better properties for making the kinds of things we want to make. So Eldwin and Yushi worked hard on a thing where we sort of start the process very much like Epi-Seal, except the first thing we do is we etch some vents through the SOI layer, and then we grow Epi up on top of that to build our device layer after having formed a chamber underneath the resonant structure that we're going to release later. It allows us to release large areas of single crystal silicon without having to put vent holes through the silicon structure. The absence of those vent holes means there's a greatly suppressed thermoelastic dissipation effect, and the Qs can be much higher, and there's a lot of other benefits that we get from this. And then since then, we've kind of been crowdsourcing the inertial sensor part of this thing. Our DARPA sponsors more or less said that we'd run our course on the Epi-Seal research side of this thing. There wasn't that much going on that looked interesting to them. If we let some other designers come into the run, they would let us keep doing it. They would continue to fund it. My students were a little upset at the prospect of having a random, unwashed horde of external designers contributing designs that might not work or might be problematic, but we overcame the issues of that, and we're currently doing this thing where every year we get designs from basically all the other participants in the DARPA funding community that we're attached to, and we allocate space in our fab runs to putting their devices in. All we really do is try to verify their parts are likely to work, more or less as they intend, and that if something goes wrong, at least their device won't wreck the whole wafer. So short of that, it's basically you throw your designs in and we build the parts. At the end of the run, we chop the wafer up and you get your stuff, we get our stuff, and we get to keep doing what we've been doing, but there's a larger community. And it's led to a lot of pretty interesting results. We've formed collaborations that might otherwise not have naturally happened. Here, working Stanford and Berkeley, bitter rivals in many ways, but happily collaborating because my friends Bernard Bozer and Dave Horsley were thrilled that they could get free parts from us that had properties they probably couldn't build on their own. So they've been building various kinds of gyroscopes that operate in interesting ways and overcome certain operational problems with MEMS performance. Our friend Farouk Ayazi at Georgia Tech, another friend but not necessarily a likely collaborator at Stanford, is participating in these runs, and we're sharing devices and getting things done together. We've worked with folks from Draper Labs on some technology that actually led to some of their DARPA funding. Our successes demonstrated in our process improved that. Their interest was in making something out of silicon carbide, but they put the same designs in our fab run. Our parts worked faster and more readily and gave them the results they needed. We've been working with Analog Devices on some ideas about inertial sensors, particularly gyroscopes, and how does the mode of operation affect the performance. In our own group and in collaboration with Bosch, we've been showing we can build multiple kinds of sensors in the same wafer side by side. What's interesting about this is that if you have a temperature sensor and a pressure sensor and an inertial sensor all in the same chip, they all measure everything all the time, right? Every sensor is a thermometer. Every sensor is a pressure sensor. Every sensor is an accelerometer. And all of their cross sort of signals actually help you calibrate the entire device and compensate for effects that might pollute a single axis device. We've been able to make magnetometers, again, lots of physics here, Lorentz forces and displacements producing a resonant signal. This is collaboration ongoing with Dave Horsley's group. So what about making inertial sensors, right? What about making really good ones? We've been, in our group at least, focusing on certain aspects of this that we think we've learned some lessons. So we want to make an accelerometer. We want it to be a resonant accelerometer. I don't want strain gauges or differential capacitance. I want a resonator. There's a history of resonant accelerometers out there in this community. They're largely devices where you have some proof mass attached to some tuning fork sort of strain gauge sensors, and as the mass is deflected left and right, there's differential axial tension on the resonators, tension or compression, which causes the frequencies to move up and down. You can measure the differential frequency and pull the signal out. There are ideas both from a lot of people around the world and more locally for sort of building mechanical levers around the micromechanical element. This is Ashwin Sesh's group, to try to amplify the strain signal, to try to make a larger delta F per unit acceleration. And there's a lot of good things happening here. But I think from my standpoint, the lesson is that all of these architectures violate one of our design rules, which is that they build a set of anchors that are kind of distributed far away from the center of the die. And they provide an access point for any of this external stress to get into the sensor and cause frequency shifts that are not from your inertial source. So we've been looking at how do we build accelerometers that have a single anchor and are resonators. So this is work under the DARPA program we've had the last couple of years. There's a big slab of silicon off to the right. It's connected to the whole die only at that left edge where I have the arrow sort of labeling the location of the anchor. There's a pair of resonant beams along the flexure that goes from the anchor to the mass. So as the mass deflects left and right, there's a differential strain on those two resonators. And really, you can think of this as being like a guitar. If you hold the handle of the guitar and shake it up and down, the different strings of the guitar are going to experience tension and compression associated with the deflection from the mass at the other end. Single anchor, micromechanical sensor. You have two resonators. They each have a differential response to acceleration and presumably a common response to temperature. And they're both as immune as possible to external stresses because the entire thing is connected only at a single point. We do mismatch these resonant frequencies intentionally because if they cross, the two resonators can couple to each other, and there could be a range where you just have a single coupled mode instead of a true differential. Because the resonators are slightly different frequencies, they do have very, very slightly different temperature coefficients, and that ends up being the residual temperature effect that we see. But this device in our lab gets down into the sub-micro-G range. And at this point, the measurements we're doing are mostly dominated by environmental vibration and the temperature effects of the lab on the external circuit, not so much on the fundamental physics. This device ought to be another factor of 10 lower if we're just talking about its thermal noise. But the nice thing here is we're in a technology. It's compatible with everything I told you about, and it's something that could go into manufacturing based on a resonant sensing of the acceleration. What about gyroscopes? The MEMS community has been making gyroscopes for almost 20 years, inspired by some automotive safety problems, and now filling up your pockets with gyroscopes that you probably have never used. Lots of different architectures, but quite generally you have the same thing where you've got a pair of masses moving in some differential motion. As a rotation signal happens, the Coriolis force couples to a differential out-of-plane motion or a differential in-plane motion depending on the vectors. And all of this is a contraption of micromechanical masses and springs suspended by anchor points around the perimeter. So when you take this die and you glue it down and you warp it and seal it in package, all of that is going to twist and stretch, and this whole thing is now going to sense all of that as well as the inertial forces. You can do pretty well. But there actually is a pretty compelling available architecture for a gyroscope that doesn't have that problem of multiple perimeter anchors. A thing invented at Boeing about a decade ago by Dorian Challoner. It's a wine glass gyroscope. So it's a flat disk of silicon with a lot of slots in it. And you drive it in plane in a mode that looks like the wine glass vibrational mode, sort of like this. And if there's a rotation around the vertical axis, Coriolis force couples the energy of that vibration into an orthogonal mode that's 45 degrees away, also in plane. And the whole thing has a single anchor right at the center. It's all in plane drive and sense. Could be made out of single crystal. It fits exactly into our process, and we've been having a lot of fun building these things. I think we may well have built 10,000 of these gyroscopes in my lab over the last decade. And if, depending on how you operate them and everything, we're now seeing rate performance down close to 1 degree per hour. And to my knowledge, this is the lowest MEMS gyro drift rate that I've seen. It exceeds anything you can buy from the companies. It exceeds all of the research that I showed you from my friends back here. Let's go back to Dave Horsley and Bernard Boser. let's see, Allen deviation. So here's Farouk's Allen deviation is maybe 0.05 degrees per second. This looks good until you look at the units on the vertical scale. The Allen deviations here go down to a few degrees per hour. The commercial parts from Bosch are also kind of in this range. Let's see, this guy gets down to about 0.135 degrees per hour. And much less effort, much less engineering, very simple central anchored device is among the best of class in this category. And lots of room for improvement here. So I think this is really kind of the story for the MEMS community. We built a lot of stuff over a lot of years that's all very cool. And it's plagued by offset and drift problems, I think largely because we built stuff with too much perimeter anchors. We've built things in processes that are inherently full of drift. And we ought to stop doing that. All right. So I got a little time left. So back to the resonators. So things we learned for sure that matter. Silicon's a great material. You can build it in Epi-Seal, has smooth sidewalls, it doesn't drift. Life is wonderful. Temperature dependence of the dynamic properties of silicon, the elastic constants are just terrible. 4,500 parts per million over the room temperature sort of operating range of a commercial product. Quartz is maybe 100 times, 50 to 100 times better. And this has always been the number one reason the quartz was the preferred technology all along. And even as SiTime was getting going, we all knew this was the barrier we had to climb. We could make stable silicon. We could do all the temperature compensation in the world, but we started out a factor of 50x behind quartz. And the time and money and effort you spend to overcome that factor of 50 is a real problem. Even if you have all this silicon manufacturing technology, wafer scale packaging, yada, yada, it's all great. SiTime spent a lot of years making parts that no one wanted to buy. We loved ourselves, but it was kind of a waste of time. The thing that changed, which actually opened this up and made it interesting and useful, was that there was a discovery that if you put enough doping into the silicon, you actually start to modify the temperature dependence of the elastic constants. In our community, this first showed up through some work from Riazi's group. But really, we were lazy. We should have been reading the literature. There was stuff 50 years ago that said doped silicon had different temperature dependence of its elastic constants than undoped silicon. In fact, less temperature dependence was accessible. We should have known this. We all should have known this 40 years ago. And that's kind of embarrassing that we didn't. But since then, we've actually, in the last decade, worked really hard to understand how to put this to use. Groups at VTT and at Stanford have done a lot of work measuring the temperature dependence of the elastic constants for different amounts of doping. We found resonator designs and combinations with orientation and doping that have much, much lower temperature dependence. And frankly, bring us to the place where the temperature dependence of the MEMS is comparable with the best quartz. So we've overcome that factor of 50 disadvantage. Now the other things actually become useful. Low cost, manufacturing, perhaps better drift. And what we've been focused on in the last few years is what about making an OCXO out of this? So the MEMS community has been talking about OCXOs a long time. This is some stuff in Clark's thesis more than 20 years ago. Polysilicon MEMS resonator, suspended on a little silicon island by some tethers that brought the electrical signals, the thermal isolation, and the mechanical support. And he had a thermistor on the suspended element. He could measure the temperature of that. He could apply different amounts of heat to the suspended element to try to regulate temperature in a fixed range and overcome the dominant sort of 30 ppm per degree C temperature coefficient of the silicon, and did quite well. There's two things here that I think I would like to see done differently. One of them is that if you make a thermistor for your temperature sensor in an OCXO, it introduces heat in one place somewhere in your system. It causes temperature gradients. It actually causes errors. You don't really want a temperature sensor that is also a heat source. It's kind of, you're fighting yourself. The other thing is you have this trade-off between the amount of stuff you isolate and how stiff your suspension has to be, because the more mass you have there, the more stiffness you need. And stiffness basically means more thermal conduction and therefore more power needed to operate this device at an elevated temperature. So you'd like to get rid of that. Spent a lot of effort in the MEMS community over the last decade on this. And I'd say the ideal resonator ought to have these properties. You don't want to use a thermistor. You want to use two modes of the same piece of silicon to measure temperature. One mode has a high temperature coefficient, one mode has a low temperature coefficient. You implement a loop around some relationship between those modes. You want to use this doping technique I mentioned to give you a nice flat spot somewhere on the temperature dependence of the dominant mode of your system and operate at that point. So you correct first order all of the temperature effects. You want to support the whole thing with a single anchor. Don't build a web. Have a single point. You want to pick a good mode. You'd like a high Q, high frequency mode that doesn't have a lot of temperature dependence to its dynamic properties. So we can fix the temperature coefficient of frequency with doping. Temperature coefficient of quality factor is another issue here. And if you're limited by thermoelastic dissipation, you've got a pretty strong TCQ, which is annoying. We found that if you build parts that are bulk mode resonators with no vent holes, you get into the limit that seems to be a Keyser damping limited. And it looks like the temperature dependence of the Keyser damping is much smaller. So you have a system that's more easily operated over a wide temperature range. You try to, again, as I said, suspend the absolute minimum stuff. Don't suspend the whole chip or a whole container, just the vibrating piece, nothing else if you can. Some of this dates back to some work we did with a different architecture some years ago. So here's what the current versions of this have looked like. We had a project just a couple of years ago where we made one of these lame mode resonators. We suspend the resonator from a single point, sort of a stub coming down from the cap. We put heat into the cap that would heat locally a region of the cap and anything attached to it. So the resonator would be suspended from that, pretty isothermal. It has two vibrational modes. One is this lame mode that has all the right properties. And then there's another sort of plate bending mode, looks like a Pringles potato chip. And it has a higher temperature coefficient frequency, and we can access these two at the same time and operate a system around that. We found from some effort that we could get to something around 200 parts per billion over temperature with this device. It took about 100 milliwatts of heat because we're dumping the heat into the cap, and there's a lot of thermal contact that allows that heat to spread. That creates a huge temperature gradient in the cap, which pushes a lot of the electrodes and contacts around and causes other problems. And what we really learned coming out of this is we got to move the heater down into the device layer. If we cap heat or die heat, we're causing all kinds of problems that are just in the way. So the last couple of years, and Liz Marie is sitting here, we've been looking at the optimal design of these in-plane suspensions. So we have a pair of anchors and sort of a slab of material that hangs off the side from those anchors. We've built folded suspensions that provide both thermal isolation and a place where we can build the heater. And then the tuning fork element hanging off to the right side is isothermal, and it's connected only at that one point. And we've been looking at changes in the size and shape of the suspension to try to optimize the contrast between stiffness and thermal isolation. And now to make the clock, we build the same technology, but we hang a frame off of this single point anchor and suspend a lame mode resonator in the middle of the frame. So its contact with the outside world is through a frame, through a suspension, to the die at a couple of points off to the side that are fairly close together. And again, we have these two modes, the lame mode and the torsional mode, that have the same operation. With the right doping, this lame mode has a flat spot at around 80 degrees C, so we can ovenize at that point. And the nice thing here, since we're suspending the minimum amount of stuff, it's pretty robust. We can have low power. It takes about 20 to 30 milliwatts to heat this thing, and it'll survive 6,000 Gs of shock without breaking. How many OCXOs in the room can survive 6,000 Gs? I don't see any hands. This can, and it's because we're only ovenizing a few cubic microns of stuff instead of millimeters or centimeters, and that helps a lot. So this is how the performance of this device looks like. We build a closed loop around the two frequencies. We apply an amount of power that keeps the lame mode at its turnover temperature and back out the signal. And what's happening in this experiment is the temperature of an oven that this is all sitting in is being ramped from somewhere around 60 degrees down to minus 40 and back up in steps every half hour. The frequency output of the clock is not moving around. There's no strong temperature coefficient. If we average within each segment, we're seeing that the output frequency is only changing by around 1 part per billion over this entire temperature range. We can sweep back and forth. It's very repeatable. If you make an Allen deviation out of the data on the upper left, there's details here that have to do with what's going on in the environment. I think the bump at about 1,000 seconds corresponds to the half-hour sort of step intervals in our temperature profile. But the main thing about this curve, and what you like to see if you like Allen deviation curves, is you like them to keep going down as you go to the right. So a little bit of full disclosure, we've done this a bunch of times. We got a bunch of data. It's generally pretty consistent, but we have some issues with the performance of our feedback controller. Things happen in the lab on an average day. Someone slams the door, someone pulls a plug. You know, it's a lab environment in an academic world, so there's glitches, and the glitches dominate what we see. But over and over again, over time periods of many hours, we're seeing Allen deviations just kind of keep going down the longer we look. There's no inherent drift, and we're able to fix most of the temperature coefficient of all this. We're looking at stabilities that are around 1 part per billion over a pretty wide range of time scales, and which get better as you go further out. So a little bit of full disclosure on this thing. The resonator and a printed circuit board live in the oven, and everything else is outside. The oven temperature is going up and down, but everything else is only experiencing the lab temperature. And we got a lot of good data back in February and March when Stanford was kind of in a crossover season and the lab was pretty good. More recently, springtime at Stanford, it's warm in the daytime and cool at night. The lab oscillates temperature-wise. Sort of the lower curve on the left is the lab temperature. We see over a week of data that the actual output sensor signal of this thing is clearly responding to that. I think all of that is happening because of the electronics in the lab and not because of the part in the oven. And again, the Allen deviation, there's a peak at 1 day, which corresponds to the temperature effect on all of the non-ovenized parts, but it looks like the Allen curve is falling off as we go out past a week. So a lot of that's fresh off the press, and I'm happy to share that with you and answer questions about it. The main conclusions are we've learned a lot about making MEMS devices in this high-temperature encapsulated process. Most importantly, we learned that silicon is great, really great, doesn't drift. If you solve the external problems, you can actually make wonderful things. This helps us build great resonators and more, I think, better inertial sensors. And I think what this is now leading back to is a possibility of building a really impressive MEMS OCXO, where you ovenize the minimum stuff, you leverage all the things we've learned about geometry and design and packaging, you build a great circuit, not printed circuit board stuff like the stuff we have outside in our lab. Obviously not optimal, but what we do is as we get started. And I think there's an opportunity to really push the needle past where Clark thought it might end at a parts per billion, even perhaps into the domain currently ascribed to the atomic clock regime. So with that, I'll stop. Obviously, everyone else does all the real work, and there's a lot of history all the way back to Aaron Partridge on this project, and I'll stop there. Thank you very much.
Thanks very much, Tom. If you have questions, please come up and to the microphones. Greg?
Okay, so I routinely fly oscillators that survive 6,000 G's of shock. We'd never get to space without them. But
cool.
I do have a question about the dual mode sensing for temperature compensation. So I'm pretty familiar with that technique. One of the things that was discovered in that approach in quartz, of course, was the dual mode idea looked really clever and worked well. But we found that over time, the differential aging between the modes would move the cancellation point. And I was wondering whether you all had looked at that same problem, or perhaps because of the temperature extreme by which you do the processing, that's your like major. Yeah. But I was wondering if you looked at that.
Obviously work in progress. Things we've seen, so we've looked at, we've built a lot of devices where we have two different resonators in the same die, and we've just run them in parallel for months and years. There's no differential drift that we've ever been able to see.
Okay.
Those were similar devices adjacent on the same die.
Okay,
this would be the first time it's actually two different modes.
Yeah, the different modes always have the tendency to age differently.
I mean, so I would say, I'll let others back that up, but we don't see any aging in any of these modes.
Okay.
So I'm hoping we won't see a differential, but.
Great talk, Tom, and thanks on behalf of the community for your leadership in this area. It's been great for the rest of us. So a question about your RXL. Have you measured sensitivity to rotational acceleration? And follow-up to that is, the single point anchor in theory is great, but it's not quite a single point when you implement it in practice. So you still would couple some residual stress.
I mean, it'll measure centripetal forces. We haven't done that test. I think we can probably predict what it will be. You could put a pair of these devices in the same die oriented, opposite directions and get a first order correction for that.
Sure. A question on the process, scaling the process further for inertial sensors, pushing towards higher accuracy. So right now the package pressures are 0.121 Pascal.
Yep.
What's limiting going lower than that?
If we go lower, and you can bake them longer in the nitrogen furnace, pull more hydrogen out. I think in general the problem you'll have is that you're in a world where there's some partial pressure of hydrogen, helium. It's eventually going to get back in unless you're going to build a hermetic, impervious seal around the whole thing. And in some ways that kind of defeats the purpose of going to all this effort in the first place. So the philosophy here is live with what you have. And at Pascal to 0.1 Pascal, I think we treat that as a boundary condition.
Sure. And then what's the largest area device that you can build? And you project a building in this process?
It's dominated more by what the cap properties are. So if we build a large chamber, it's basically like a ballroom with no pillars. The roof will sag under static pressure. So we have design rules for putting beams. It's very much like an architect would require. We've built things that are in sort of 5 to 10 millimeter range. I think it's just a question of how much real estate do we want to waste on a single idea in our process.
Yep. Thanks.
Okay, cool. Thanks, John.
Yeah, your presentation show a great improvement and more advanced into long-term stability and temperature stability. How you aware of any effort in industry or in academia on the short-term stability, such as thermal, noise, or random walk? So yeah, short-term, to do that well really requires integrated circuits and a whole layer of technology that in my mechanical engineering group we don't attempt. I think we could spend a decade doing a really bad job at that. And so we've kind of resisted, and we live in this printed circuit board external world, which clearly limits our short-term behavior. I'd say that's a great question to ask at the SiTime talk this afternoon, because there the ASIC, the BiCMOS process, and everything they build around that is targeting that part of the problem as well as our end. So it's doable, it's just not our core strength.
Tom, thanks for the great talk.
Thanks.
I have a follow-up question to that. Based on your current resonator queue and the interconnects into it, have you calculated what the drift would be if you actually expose the circuit to temperature? And what techniques do you think are needed in the future to compensate for the drift of the electronic circuit in the oscillator?
So we did a pretty thorough analysis of all that about 10 years ago as part of Jim Salvia's thesis, which was a similar idea but a slightly different detailed architecture. And it comes down to the temperature coefficient of some of the passives that we use as part of the feedback elements in our first stage transimpedance amplifier. There's gain and phase changes with temperature that feed into the loop and push the frequencies around. That is, I think, fixable in the domain of a good ASIC. And I think making better and better printed circuit boards is really kind of a fool's errand there. What we can do in the short term is, and we're doing this now, we're moving different parts of that infrastructure in and out of the oven to see if we can identify for sure which exact piece is causing the problem, and then do models around that to see if we can make claims about where we can make better improvements. But I think ultimately the right place for this is to be married with a good ASIC. Thank you so much for all the time and energy.
Any other questions? Oh, thank you. I think
Oh, sorry,
we might have time for one more question.
Okay.
Yeah.
Thanks for a great talk. It's in relation to what you just mentioned with regards to having a great ASIC. Obviously, this process works with a diverse range of applications and a certain flow with sticking to the physics. Has there been any exploration with regards to integrating with CMOS or different materials, different processes? Are there any challenges that you've sort of already experienced or that you foresee that need to be overcome? Just curious on what you think.
So it's possible to build CMOS on top of this technology. So at the end of the MEMS process, you have a sealed silicon wafer. It's already been through 1100 degrees C temperature budget. And there are parts of the field that could be good single crystal, depending on how you deal with certain parts of the design. And so you could take that wafer and run it through a CMOS fab and build good CMOS on that. And we did it at Stanford in a sort of a lousy CMOS some years ago. Others have tried it elsewhere. I think, so it's a doable thing. The reason it's not done generally is more practicalities, that the size of the MEMS and the size of the CMOS don't match up well, and you can't build them really on top of each other. So you end up wasting a fair bit of real estate in both processes. And you just don't get that much benefit from it that you can't overcome with some good flip chip or other sort of modern techniques for putting those together. And SiTime could talk to this in great detail, but generally let the MEMS people focus on building the great MEMS wafer. Let a company like TSMC or Global Foundries build you great CMOS. Focus on design, and then put those together at the end, and you get out of a whole world of multiplicative yield and sort of compromises on technology. So it's doable, but just not really a great idea.
All right, let's thank Tom one more time.
Thank you.
Thank you.
Thanks again.
Because of the timing and the fact that they need to split this room in two, we're going to